Good morning, good evening, everyone. My name is Kostya. Uh, the talk I'm going to present now is a little bit unusual for me. I usually talk about things I and my team has done, and this time I will be talking about things me and my team have not done yet, or not at all. So, as a way of introduction, here is a few things that my team and our sister teams has done in the past. So, more than a decade ago, we started tools that have an umbrella name sanitizers. You may have heard about ASAN, TSAN, MSAN. We have similar tools in the kernel space. And quite soon we realized that these tools are not finding much bugs unless we force the software to trigger those bugs. And this is how we came to be interested in fuzzing 6 years ago, probably. And we have developed a few tools in this space: libfuzzer, syscaller. We have partnered with the Chrome security team to launch OSS Fuzz. Also implemented libprotobuf mutator, GoFuzz, and a few other tools in the space. If you're interested in the details of how fuzzing is used in Google, you can look at the slides from the Shonen meeting last year. Marcel has spoke about this meeting already. And I'm actually not actively working on any of those tools for the last couple of years. We keep maintaining them, keep improving slightly, but no really active research. I am, however, building a specialized fuzzer for a proprietary system. I cannot talk about it too much, but I'm doing some really interesting fuzzing research that I hope to talk about in a couple of years. Fuzzing is not the end of the story for us. We also invest into hardening in production, for example, various flavors of control flow integrity. We're very active in the space of testing the production software, and you can look for GWIP ASAN. It's our new toy that finds bugs in deployed software. And finally, we're looking at hardware-assisted memory safety. For example, we have partnered with ARM to add an extension to ARM to find memory safety bugs in deployed software. So with all those things, deep fuzzing remains very interesting, although probably not the most important. So let me first define what do I mean by deep fuzzing. I don't think anyone knows what it is. I don't think I know what it is. I only have some ideas. So ultimately, we probably want to find more bugs, and the more bugs we find, the deeper the fuzzing is. But the number of bugs is a very misleading metric. Like, what if our software doesn't have bugs? Does it mean that we cannot fuzz deep? Probably not. So usually when we talk about deeper fuzzing, we mean we want to discover more control flow edges, we want to discover more code paths, more data flows. I'm not even sure you can use this term in plural. And ultimately, we want to find more of something else. And for me, the question of deep fuzzing is the question: what else can we find? I want to emphasize that for very practical reasons, like if we want to make our software more secure, then deep fuzzing is not the most important. I would say that the more important are things like fuzzing wide, fuzzing often, fuzzing incrementally, fuzzing early, fuzzing naturally, and fuzzing young. Like I would actually emphasize the last two bullets. Fuzzing naturally, I want to see more programming languages where fuzzing is a first-class citizen. even Rust doesn't come close to that. I want to see better attempts. And fuzzing young, I want fuzzing to be in everyone's CS curriculum. Still, I'm here to talk about fuzzing deep. First of all, because there are lots of existing fuzz targets. Attackers are actively trying to find bugs there, and the code owners need to be ahead of them. And of course, there's a lot of fun research. So, since this is one of the last talks in the conference, I hope most of you are already aware how the guided fuzzing typically works, but I will still quickly repeat it. First, you're supposed to acquire the seed corpus. So this is the set of inputs for your target that are representative in some ways. Then, in an infinite loop, you have basically 4 steps. You choose an input to mutate or several inputs to cross over. Then you do the mutations or crossover. I have a question. Google should have an impact on Golang then. We have an impact on Golang. We have implemented GoFuzz maybe 5 years ago. And we have recently enabled fuzzing in Go as a first-class citizen. So thanks for the question. Anyway, back to guided fuzzing. You have to choose the inputs, you have to mutate the inputs, then you have to execute the mutant. And while executing, you have to collect the control flow, the data flow, whatever else, if we find out what else to collect. And of course, we find bugs. And the final step is to update the corpus. We maybe expand it and maybe shrink it. So I hope this is not controversial for most of you. Let's speak about the first item, acquiring the seed corpus, which most of the research neglects, sadly. It has been an old custom, at least at Google, that if you are fuzzing a file format parser, you just crawl the web to find the inputs of that type. And this has been vastly successful. But since then, fuzzing has moved from fuzzing just the file formats, which is kind of a well-polished problem, to fuzzing other things like rich APIs. And for that, you cannot crawl the web. You cannot crawl the web for sequences of Linux system calls, for example. It's hard. And so we need to find and polish ways of acquiring corpora for all of the fuzz targets we have. One of the approaches that we are somewhat actively using is to use the corpora from other fuzz targets. If you're fuzzing A, you may as well find the corpus from B useful. And I have a couple examples here. First, amazing example that we had demonstrated last year is we have found a few crashes in the Windows USB subsystem by fuzzing the Linux USB subsystem. The subsystems are completely different, but they implement the same protocol. And so you can use the corpus from one to fuzz or just to test the other. And we had several similar examples in OSS fuzz when one fuzz target produces interesting inputs for other fuzz targets from completely different projects. Another area of work in the seed corpus space is monitoring the live system and scavenging interesting inputs. And this is where I usually say that the user is the ultimate fuzzer. No matter how well we fuzz, if we have a billion users, the billion users will find ways to surprise us. And we do a little bit of that, but it is pretty complicated to have this feedback from the production system back to the fuzzing to testing system. First of all, the production system typically has huge traffic, and we cannot just dump all the inputs, so we have to choose interesting inputs. And how do you figure out if an input is interesting if the production build is not instrumented? Then there is, of course, all kinds of issues with shipping production traffic back to testing environment, like privacy issues. And we currently have no ways to automate it. All our efforts in this space are one-off cases. Which reminds me that currently we have fuzz targets that are typically written as unit tests. So these are test-only pieces of code. And if we want to scavenge inputs from production, we have to better integrate fuzzing and production code. We are being successful in a couple of cases when we have actual bugs in production, and we are able to use the triggers for those bugs to enrich the fuzzing corpus. However, these are one-off success cases, and we really need to find some kind of automated way to do this. But enough about seed corpus. Let's talk about the while true, which is not actually a step; it's just a construct in my slide. But still, it is somewhat interesting. And the frequent question we get is, when do we stop fuzzing? And we often get this question not from the software engineers, but more from like program managers who care much more about the resources we're going to spend. And our frequent and naive answer is never. You never stop fuzzing. And our explanation is threefold. First of all, the more time you spend on fuzzing, the more chances you have to find something. And then, of course, the tools evolve and the code evolves. And so you still have to do fuzzing 24/7 forever. But if the code and the tools actually do not evolve in some time frame, then running fuzzing in an infinite loop starts bringing diminishing returns. And if you care about a single fuzz target, it doesn't matter, you still fuzz. If you care about 10,000 fuzz targets, and you, as always, you have limited resources, you actually have to answer the question, how do we know when to stop for the particular fuzz target? And then if we did stop, how do we know when to restart? Of course, if the code changes, we need to restart, but maybe the tools have evolved. Maybe the tools are now better. How do we need to? How do we know we should restart? And for the large fuzzing ecosystems like OSS Fuzz, this question starts to be very interesting because the cost now begins to be visible. The next part is choosing the inputs. And I'm not actually sure this is an important part, but let me describe it. So suppose we already have a corpus. It has k inputs, and our goal here is to compute weights for every input and use those weights to choose the inputs to mutate. And the very naive approach is just have the uniform inputs. And in my practice, this doesn't really work well, or at least in short runs, we see it not perform well. LibFuzzer by default uses another naive but more productive approach. It prefers the most recently added inputs. There is some logic behind it, but it is still pretty naive approach. And with Marcel's help, LibFuzzer has recently acquired another piece of logic that's called entropic, and it favors inputs with infrequent control flow edges. I'm oversimplifying it, but roughly it is that. And the question that I still don't know the answer to, is it actually important? Interestingly, when we compare entropic with libfuzzer, on relatively short runs, like hours or days, we see very considerable improvements. Like entropic works well in the short run. We don't have the sign of improvement in long runs. We're talking weeks and months. And I don't actually know whether there is no improvement or whether we just don't have instruments to see it. So the question remains, do we need to dig there? And if we have to dig there, how do we measure the success? This is one of the research problems we have. Interestingly, most of the research is focused on mutations and choosing inputs for mutations. And I don't remember any recent research at all on crossover and on choosing pairs or tuples of inputs for the crossover. I don't even know if it's important. Okay, switching to even more interesting, mutation crossover. We already had talks about structure-aware mutation. It is pretty important because most of the inputs are not bags of bytes, but are a highly structured input. It could be a syntax tree, it could be a graph. Inputs could be partially compressed, partially encrypted. Some of it can be protected with checksums. And so we need a way to have mutators that are not breaking the structure. And you already heard about libprotobuf mutator. I know there are mutators for similar data structures like thrift. And these things work amazingly well when the input for your API is already protobuf. And it works reasonably well when the code owner has time and skill to describe the API or the input as a prota. You have seen a great example of this an hour ago. Another great example is sockpuppet. It's a bug discovered by my colleague about a year ago where he described the API as a protobuf. But this is very time consuming, and we need to find a better way to automate it. Another example is syscaller, where we hand code the structure of the API. Again, this is very time consuming. We need to find ways to automate it. And I see I'm already being short of time, so we'll accelerate. One of the important things that we don't know how to do is guided mutation. So we talk about guided fuzzing often, but our fuzzing is guided mostly in terms of corpus expansion. We know when to expand the corpus. We don't know how to guide the mutations. libfuzzer, AFL, honkfuzz do a little bit of that. For example, with interceptions of memcmp and strcmp, but they're not doing it enough by any measure. We have a prototype of, we call it data flow trace guided fuzzing, where we capture the full data flow trace, and then we will guide the mutations based on the data flow trace. This is a prototype. It's not production ready. Much more research is welcome. And of course, an extreme case of guided fuzzing, guided mutations is symbolic execution. It has lots of its own scalability challenges. We don't even have anything in terms of research for guided and structure-aware mutations at the same time. It's an open topic. Please contribute. How to choose a sequence of mutations is another interesting topic. There are plenty of papers. Some of them are using ML. I don't know if any of this is actually working at large scale. I'd like to hear from the authors, from the users. Next step is execution. This is probably the most interesting at the current stage. So first of all, we want to find bugs, and we know how to find memory safety bugs. We know how to find assertions. But do we know how to find logical bugs, for example? Differential fuzzing is probably the only way currently used to find logical bugs. Can we do more than that? More or less all guided fuzzers are collecting the control flow. Can we do better than we do now? I think we can. First of all, we need to get compilers on board. We want to get more sensitive, more detailed signal from coverage instrumentation. And we also already know how to use someone else's control flow. Again, this is differential fuzzing, and the paper called Nezha is doing a very good job at giving us an idea of how to use someone else's control flow to guide our fuzzer. Data flow. Data flow is almost entirely unused by the guided fuzzers. We have a couple of examples where we're just trying to do a little bit of it. Laugh and Tell paper translates data flow into control flow, and LibFuzzer translates data flow directly into the bitmap internal to fuzzer. But these are baby steps. Data flow is probably even more important than control flow, and we're almost not using it. We need to find other signals, and perfuzz, which Caroline may talk about it in a few minutes, uses time and space overhead as a signal. LibFuzzer uses stack depth as a signal. What other signals? Please help us find other signals. And the basic requirement here would be that the amount of signal has to be linear or not much more than linear. We cannot use exponentially expensive signals like execution paths and execution traces. At least I don't think we can. Finally, updating the corpus is also an important step. I want to praise one of the recent paper called Anku, which uses which tries to maximize the minimal distance between the corpus elements. It's very different from what most other guided fuzzers do, and I believe this approach is worth further research. Can we do much else? I don't know. I would like to find it out. Fuzzing stateful systems is a mess. I'll skip the slide. Evaluating fuzzers is a mess as well. Our sister team has launched Fuzzbench recently, which is a large-scale benchmarking ecosystem for fuzzers. It still has at least two things that I would love to improve there. First of all, any meaningful evaluation of fuzzers is very CPU intensive. And currently we're just spending these CPUs to evaluate fuzzers. I would like to combine evaluation of fuzzers with useful work, and that's going to be very tricky. And of course, I think Fuzzbench is currently missing a way to evaluate structure-aware fuzzers, like anything with protobuf mutator and something else. And finally, human in the loop. I think we are undervaluing ourselves and what's between our ears. We can put our brain to work to improve fuzzers, but we need to be very focused, and we lack the tools to apply human brain to fuzzing. So to summarize my a little bit messy talk, I see quite a few challenges in deep fuzzing. And if you want a very short list, it would be acquiring a better seed corpus, guiding mutations, finding ways to expand the corpus smarter, and finding ways to put the human in the loop. Thank you very much.
both in the Slack and in the chat. One of the questions is, do you have any pro tips or rules of thumb for recent papers that are actually trying to get deeper into the code base?
Sorry, can you repeat it, please?
Do you have any recent papers that are actually trying to get deeper into the code and not wider or faster, but just deeper?
Well, there are lots of papers that try to do that. Most of the papers try to do that. And most of the papers use the evaluation techniques that are hard to trust. And so this is why Fuzzbench is so important, I think. And given the number of papers that I've read, I cannot even tell which of them are good because of the problem with evaluation.
All right, that makes sense. Okay, another question was, will there be a recording? Yes, of course, there will be recordings. You mentioned briefly symbolic execution and its scalability issues. Do you have any faith in the approach, or do you use it in practice?
We do not use it in practice. I mean, I don't use it in practice. Maybe someone is using it at Google for very, very specific cases. We're waiting for breakthrough in the technology. I don't see the current technology being scalable. I believe there will be breakthrough. Lots of people digging there.
All right. Since we're over the time already, I would say if you want to, please answer the other questions in the Slack. And thank you for your talk so far. And it's time to introduce our next speaker. Thank you, Kostya.